All right, here we are. Let's keep cooking along. If I can get this open. Okay, so let's take a look at the next differential equation. So we're going to find the general solution of this equation, which again, we're looking for some function that would make this true, right? That's what solutions are. What makes this true? So we're trying to find some function, y equals something, that has this condition that y minus 2 equals x times the derivative of y. Okay, so the first thing we do is we separate the variables. Right now we have dx, dy on the one side, and with our x, and then we have y on the other side. So we need to get dx up out of the basement. So this is going to end up being y minus 2 times dx, just not going, there we go, and then x dy. All right, and then we're going to divide both sides by, we'll divide by x on one side and divide by y minus 2 on the other side. So we're going to end up with, and notice I'm writing an arrow, not an equals, because we just don't want this run on equals, but this then lends to dx over x equals dy over y minus 2. Okay, now we can take the integral of both sides to undo that. So, well, what's the integral of 1 over x? Well, it's ln of the absolute value of x plus c. We're going to put the plus c just on whatever side x is on. That's fine. And then the integral of 1 over y minus 2 is ln absolute value of y minus 2. And now how do we get y by itself? Well, we have to raise both sides e to the ln. Now, functions do not distribute. Okay, I'll say it again. Functions do not distribute. So this isn't just, this isn't e to the ln x plus e to the c. Okay, remember functions don't distribute like that. But we can use our exponent rules for that. Now, in this case, see, since this whole thing is one term, the e undoes the ln, and all we end up with is absolute value of y minus 2 down here. Now, remember our exponent rules say that if we have e to the a plus b, that's the same as e to the a times e to the b. Okay, so that's the same thing over here. That's same as e to the ln of absolute value of x times e to the c. Okay, and e to the ln of absolute value of x is just absolute value of x, because the e and the ln now cancel each other out. And now think about this. What is e to the c? Well, e is a constant, and a constant raised to a constant is a constant. So you see this? We have a different c, but still a c, right? This is just any c. Okay, and that's absolute value of y minus 2. I know it feels like a little math of magic that we can just like, poof, e to the c becomes c. But it's still a constant. We just don't care what that constant is. It's just a constant. Okay, now you're like, how do I get rid of the absolute value? Well, absolute value means plus or minus, right? Absolute value means either it equals positive c absolute value of x or negative absolute value of x, right? Okay, so here's another mathemagic question for you. What is plus or minus c? It's still just a constant. It doesn't matter if c is positive or negative. So, poof, our absolute values are gone, because now, instead of c2, we're just going to call this c3 because it's another constant. We have y minus 2. Because positive c and negative c are both still just a c value. Okay, and then I add 2 to both sides, so I get c3 times the absolute value of x plus 2 equals y. So there's our general solution for this equation. Let's see. Oh, and then it asks for our particular solution. And actually, we could undo these absolute values as well. So this is just cx. Oh, cx. So there you go. Now we're looking for our particular solution. What is the particular solution when x equals 1 and y equals 1/2? Okay, so that just tells us when x equals 1, y equals 1/2. So I have cx plus 2, that equals y, and y equals 1/2. And then c times 1 plus 2. So 1/2 equals c plus 2. So I subtract 2 from both sides, and I get -3/2 equals c. So I just plug this c in back in here, and I'm going to get y equals -3/2 x plus 2. So this is the particular solution. Now remember, this is our general solution saying that this is a family of functions that fit this differential equation. And now this is the exact function. So these are some lines, right? Some lines. And this is the exact line that fits this differential equation.